we have 32 projects for the last 5 years. You can see what we had. I am the coordinator of most of them. Of this one, with it is extended. It started in 2016, but it is extended. It's a very interesting project with China, India, Malaysia, Israel. Pay attention, Malaysia and Israel working together. So this is, and we worked very, very well. The other one is with Mongolia, also very successful. Sector Skill Alliance, I hear in it, I wrote the partners because not the countries, but these are pure European, only countries from European Union can participate. And here we have the largest companies in micro and nano electronics involved in this project in Finland, Austria, IMEC, Bosch, Dresden, Jeep Design, etc. And the new one project that I'm coordinated is also in a program support for policy reform in this. So within this project, I'm invited. Unfortunately, it takes a lot of time, but I'm invited in most of the meetings of the European Commission, because it is about policy reform, how to improve the professional education, the vocational education in Europe. And it will start now, this with Albania, and the most important project, of course, is our Spacecom, and I am very, very happy to be part of this consortium. So what our laboratory does, these are the one area is micro nano electronics, the other is different, the new educational technologies, performance support systems, integrating learning and knowledge management systems. About e-learning, we started, unfortunately, e-learning, this is something very important. I want to say distance education. I studied also distance education at the University of Distance Education in Spain. Unfortunately, it is not so successful. Only 10 to 15% of the students can graduate. So, and mostly for engineering education. Let's hope to have very soon opportunity to have face-to-face lecturing and mostly laboratory practice, because this is very, very important for us. Who am I? So this is my education. I studied automation and telemechanics from the Technical University of Sofia, then a Master Science degree in Educational Technologies at the University of Twente in the Netherlands. And I made the doctorate, and I'm Doctor of Science in Microelectronics from the Technical University of Sofia. My positions, I'm professor at our department, but I'm teaching mostly. I teach mostly in the French department, head of the Taylor Laboratory, and was invited professor. I spoke about this. These are my research interests, and I'm proud of my language speaking. Okay, thank you for your attention. Now I will continue with the presentation on just on the introduction to microelectronics for information and communication technologies. It is micro. Okay, what is micro? What is nano? This difference is very important, because nano electronics, what is accepted for nano electronics, this is already under 100 nanometers. So 90 nanometers was called already nanotechnology. First electronic digital computer. Yeah, I'm proud to say it, although the Americans don't recognize it, was Bulgarian. John Vincent Atanasov, he was born in Bulgaria, but he was living in the when he together with Clifford Berry, when they invented the first computer in 3742. He was in the United States. So the name of this computer was the NASA Berry computer, or because of their names, ABC. It was called ABC. Sorry?
No, sorry.
Okay.
Technical.
So what is specific? What was it's specific? It was not like nowadays computers. It used regenerative memory, regeneration. So it was dynamic. There was parallel processing, what is typical for the a machine to be called not calculator but computer. The arithmetic was binary, and split computing functions, routines, away from memory use and management. But it was not programmable. It could only solve simultaneous equations problems, but it is still considered as a first computer. The journey started in 1995. Why we call it journey? Because Fairchild Semiconductor created the first integrated circuit. Then the first microprocessor of Intel, not of Intel, the first in the world, was created in 71. This is just one example. Pentium 4 of Intel. A little bit history. The first calculator. The first calculator was called Babbage, differential machine Babbage, in 1832. It was a calculator. Just a picture how the first computers looked at the beginning. Enormous hole full of ENIAC. It was the first electronic computer. So revolution came with the invention of the transistor, the first transistor of Bell Labs. Can you imagine how it looked in 48? The first transistor, why transistor? Because there were three gates. So the revolution, how it, the development in 49, Shockley invented the bipolar transistor, the logic gate. What is the basics of microelectronics, created by Harris in 56, the first monolithic integrated circuit. So this information is what I got. From different sources, but I'm not sure that it is not manipulated by Americans. So what you can see, there are only American names. There could be some differences. So that's why I say that this is what I found it as their information, but could be some differences. So okay, the first monolithic, but that's good to know the name. Maybe they are Nobel Prize laureates as well. The first commercial integrated circuits logic gates in 60s. Then we had different logics. Transistor logic in 62 until 90s, ECL. So this is history. I never speak about this. My students I speak, but just to know how it was. Okay, some more history. The MOSFET transistor. Canada. Can you imagine someone who is not was not American? It's Lilienfeld in 25. But okay, transistor. You see that this is before they worked on it. These were physicists. They worked on the theory, but it is not. It was not still a transistor. So PMOS transistors were used at the beginning, then NMOS, because the speed was higher from 1970s. These were the Logix 4004, 8080, and CMOS in 80s. Until now, we use this technology. Because of power benefits, what was the benefit? It was usually the power consumption raised with each new technology. It raised because the integration raised, and we had the more and more transistors in chip. Only with the CMOS technology, we could save some power. Why? Because I think you know that it's based on the inverter, and you have two transistors, one P channel, one N channel, and they consume not only, of course, but mostly the consumption of energy is when they change the level, when they change the state, and not during the whole time of working of the system. So we still, there is still some use of bipolar technology. This is BiCMOS. Sorry, it's okay. Yeah.
Again, technical.
Okay, so BiCMOS, gallium arsenide, silicon germanium, gallium arsenide, silicon germanium. Okay, but gallium arsenide is has very high application and in space technologies as well. This is a composite semiconductor. I worked part-time in one American company for the design of integrated circuits on gallium arsenide. It was for 3 years, part-time. So it was very interesting for satellite systems. These are really, but it is much more complicated. The design, the application, and the fabrication is very complicated. That's why it's used only for space technologies, military purposes. Unfortunately, as you know, all new, the highest investments are in these industries. So we have 3-gate is the basic technology, but it's not 3. It's not 3. It is, they call it is TRI. 3-gate by Intel of 2016. Nowadays, you see, I will make, I found a movie. Also, Intel is not leading in technologies. Intel couldn't develop its, even 10 nanometers was not successful. They intended to go to 7 nanometers technologies. They didn't succeed, and the best is now a Taiwanese company from Taiwan. I have also a movie on this. I don't have it, it's on YouTube, of course, but I will show you this and how they advanced in the technologies. Something very important that I want to stress, and I explain always this to my students. Nowadays, we speak about technologies, nano nanoelectronics. What we say, this is 22 nanometers technology, 10 nanometers technology. What is it? What is it? This dimension? Where are these 10 nanometers? 5 nanometers. 5 nanometers is the top nowadays. In iPhone 12, you have already technology. The processor is on 5 nanometers, but it's fabricated in Taiwan. This is the length of the channel of the MOS transistor. This is the shortest possible distance. The length, usually the channel is wider because of, okay, this is very, very, very deep already science on microelectronics, but this is not microelectronics, this is physics, and I think all students, they studied it, but this is very important to know what it means. And that's why I'll show you in the presentation on displays, for example, because our students, they are very, very intelligent, and at least even if they are not experts in some area, they should understand the basics and not to trust easily to the commercial information. I'll speak about it later as well. So, okay, this is the one picture of the first integrated circuit, bipolar circuit. It is of Motorola by 1966. Okay, we saw this Intel microprocessor with 1,000 transistors. It is fun now with milliard transistors that we have, but can you imagine what it was by that time? It was great. And 1 megahertz function. I have some in French. I'm sorry, maybe there is some information in French on my slides. So Intel Pentium already, and this is i7 6-core processor of Intel. Of course, you can't see anything. We have, I think even there we had about 2 million transistors. We had shared cache and memory controller, and this is the main organization on the chip, the integrated circuits. And i9 was with the last Intel processor with 18 cores already, and maximal turbo frequency 4.2 gigahertz. The die map, it looks beautiful, but the design, you can't imagine how difficult it is. The development of 5 nanometer technology, okay, it started, let's say 5 years ago. IBM research in France, in Grenoble, they worked on this as well in COA, this is Minatech. And they had successful circuits, but one thing is to have something working in the laboratory, in laboratory environment, and something completely different is to create integrated circuit with it, because one transistor could work with 5, 10 transistors, yes, but when there are much more, there are a lot of other problems. There are noises, there are parasite capacitors, and heat evacuation, and the way to the market, to the foundry, and then to the market is very long. So they didn't arrive. IBM worked on it with 5 nanometer silicon nanosheet transistors. Yeah, the enhancement is much higher, but and I want to say something. Why I love my job, because not only students can learn something from me, but I also learn from my students. At the beginning of each semester, I study what is the newest on the market, and not only on the market, in the research. And I followed because leaders were Intel. Intel was the leader for maybe 20 years in technologies. And I was checking 3 years already, there is nothing from Intel, nothing new. And during my first lecture, one of my students said, because I don't use iPhone and I don't like using iPhones, and I use Samsung, and when I will present the displays, you will understand why I buy this, the newest editions of these mobile phones in order to check the technology. And iPhone, Samsung are the best in screens, in displays. That's why I bought Samsung S10, for example. But my students told me, Professor, we read that iPhone 12 has already processor on 5 nanometers. And then I was very happy. So I learned something from my student, and I went looking on internet and I found who, because I know that iPhone, they don't produce anything. They buy, or maybe they design something. Yeah, they made a design, and the fabrication was made in Taiwan. And what is also very interesting, you see this company is governmental, it's not private. What is also exceptional for all these companies, usually they're private, and this is great that the Taiwanese government is supporting the research. This is how a silicon wafer looks. I will show you now a short movie, how the circuit is done. But this is a silicon wafer. It was silicon 30 millimeters, 30 centimeters, excuse me, 300. This is the last technology since 12 years, maybe. Again, in Taiwan and in Singapore, they are working on 45 centimeters diameter. This is enormous. Why is it so difficult? Because all processes are at the same time for all. You can see the die, one chip here, the small die, single die. And on one wafer, we call it wafer, we have a lot of integrated circuits, a lot of dies. After all processes technological are done, we cut the silicon wafer, and it's cut with diamonds or with laser. Nowadays, laser is used. Here you can see AMD Athlon. It was the processor of Infineon Technologies. I was very proud with them because this is European company. It was European. Nowadays, with this globalization, who knows? But it was German company, and AMD was made in Munich. Then they stopped. They decided not to invest in foundries because I told you, for each new technology, new foundry is built, and it is extremely expensive. It's worthy only when we have a very big market. If we produce millions of circuits. Moore's law, the law of Moore, you know, I think he predicted that he's still alive, what is very good. I found his speech in YouTube, and I'm very happy that this man that we cite all time is still working and still teaching. He predicted that the number of transistors that can be integrated on a die would double every 18 to 14 months. It happened. But last years, it's a little bit, the law, it slows down. Many people said that consider that it will stop working. We will arrive at we are on the edge. but we still continue going down. Of course, when we arrive at the dimension of the atom, it will be the end of this technology. That's why a lot of I will not show now the movie because we'll see later. So power density, I spoke about this when I spoke what is our research. So you can see power density. This is watt per square centimeter, because this is the power dissipated on specific surface. You can see what happened in the years. So here we are when we could save some power evacuation. It was with CMOS. It was NMOS to CMOS. And then we went up. And there is, for now, we are still on CMOS. And the power density is enormous. This is, can you imagine, 1 kilowatt per square centimeter? And we have to evacuate this heat. The tendency nowadays, it's related with this, with evacuation of power. The tendency is to reduce the power supply, and it is done. It is already at 0.7 volts, but it's still a problem, the heat evacuation. These are not only the nanometric technology is so important, but also the packaging. That means putting these dies, the silicon dies, in a corpus, to protect them and to put them on the printed circuit board. System trends, you can see we go to all-in-one products usually. Even now they say that the telephones can be used as computers. I don't agree. Without a keyboard or without a mouse, how can you design a circuit on a phone? It's impossible. So miniaturization of the systems. You can see how we started in 70s. You saw before it was ENIAC in one big hole, and nowadays we have biosensors, smart watches, etc. Some interesting facts. I will not read them. I will leave you reading them. They are really interesting. Yeah, these were the milliards in with 4 cores. It was 6-7 years ago. Yeah. I hope you read it. That's interesting, no? What we have, the population of China in like this in one chip. So I should make different, I should share in a different way, I think. Just, why it's written screen? And there was a way I want to share also the sound. I'm not sure. I share sound, okay. Okay. What happened? It doesn't, okay. Strange. I'll try again. Can you see my screen?
Yes, it is on PowerPoint.
Only PowerPoint, but not when now. No, not. I don't want to go to Zoom.
Yeah, we could see your browser also.
My browser, but I want to go to it. Okay. Ah, no. No, thanks. Okay, but the publicity, I'm sorry. It is made by sound. No? By Sam, excuse me. How they made the wafers? The sand is melted. How they made a lot of kinds of photography to make masks through many other processes to change the conduction. It's ready, the wafer. Now, diamond dividing. Chip is taken, dice are taken away. Before to take them. We'll now make, so I don't know, to continue a little bit with the fabrication. I have also one movie in Russian to continue with it, or to make a break and to continue later. What do you prefer? I will show another movie, huh?
Yeah,
Okay.
I think this is a movie, so we can take a rest, like watching it.
Okay.
What we, for the sake of convenience, call a chip is officially called an IC, the abbreviation for integrated circuit. A chip is like a city with no people but bursting with activity. A chip is packed with industrial buildings, control centers in the form of components such as transistors and resistors, which together form one huge network. The chip's infrastructure carries vast amounts of fast traffic along roads and communication networks. The building blocks in chips are not only becoming ever smaller, but our designers are also making the chips cleverer all the time, so as to create new possibilities continuously. This makes the equipment controlled by these chips better, safer, easier to operate, more energy efficient, and friendlier to the environment. Let's stride in 7-league boots through the ingenious process by means of which products such as chips are produced at Philips Nijmegen. We'll explain aspects such as the most important steps in the production of ICs, and to make this easier to understand, we'll begin with a series of animations. A chip is an extremely small silicon plate, ranging from a couple to several dozen square millimeters in size. This tiny silicon plate is then filled up with a great number, sometimes millions, of microelements such as transistors, diodes or resistors, which together form an integrated circuit, the IC. We make a large number of chips all at once on a round silicon disk called a wafer or slice. First of all, we create a new layer of silicon on the slice, 1/100th of a millimeter thick. We then oxidize this silicon layer in an oven so that an even thinner insulating layer is created on top of it. We then apply a coat of light-sensitive lacquer. We expose the lacquer through a kind of photographic negative so that the lacquer dissolves in certain places. Then, in the places where there is no more lacquer, we shoot atoms with great accuracy through the oxidized layer into the silicon. The layer of lacquer is then no longer required and is therefore removed from the slice. We then ensure that the atoms penetrate a little deeper into the silicon by a few thousandths of a millimeter. A new silicon layer is applied over the oxide layer. And once again, a layer of lacquer is applied, exposed, and developed. The silicon which is uncovered by this process is then etched away. Another series of treatments involving lacquering, exposure, bombardment with atoms which penetrate the silicon, new oxide layers, etc. is performed until the whole pattern is complete in all its layers. Some 300 to 400 process steps are required, along with 15 to 20 different masks with microscopically small patterns. The final step in the process is the connection of the various, almost invisible, tiny elements in the silicon. This is how we make an electronic circuit, an IC or chip. Naturally, we have a particularly good relationship with our suppliers, as they too play a part in determining the final quality of our products. Silicon is made from ordinary quartz sand, and rods of silicon are then created, or drawn, at extremely high temperatures. Thin slices are then sawn off these rods with great accuracy. The ICs will be produced on these slices of silicon, for which purpose the slices will undergo 300 to 400 processes. The first step in the production process is as follows. In this special oven, the slices are covered by a new thin layer of very pure silicon, into which the transistors and other components can be built. The slices with a new layer of silicon are placed in other boxes, where the silicon is allowed to oxidize. This insulating oxide layer can be removed at a later stage when necessary. These are known as the yellow rooms. Here, extremely intelligent, fully automated machines are used to apply the light-sensitive layer of lacquer to the oxide on the slices and to expose the slices. Yellow light is used in these rooms, as the lacquer is not sensitive to this. The patterns on the masks, a kind of photographic negative, are of course designed by our own development engineers. The templates themselves are made by other specialists. It goes without saying that we also cooperate very closely with these suppliers and equipment manufacturers. In these so-called implanters, specific atoms can be shot into the unprotected areas of the silicon to give them a positive or negative conductivity. This is done incredibly accurately. For example, 1 atom in 100,000 silicon atoms. One of the next steps in the process is etching, removing material locally from the slices with great accuracy. This department uses an automatically controlled process involving acids and caustics. Another technique used is dry etching with an etching gas. This picture gives an impression of the technology involved in this dry etching. All of the process steps we've seen, and many, many more, are repeated until the product has been fully assembled. This is what the smallest parts look like through a special electron microscope. Sometimes, the chip designers use a technique in which the chip is sawn through, so you can even look inside. The last step in the process involves making connections between the various elements in the silicon. These are so tiny that a minuscule vacuum-deposited layer of aluminium is required to make them. The innumerable processes, which take approximately 3 weeks to complete, are concluded by an initial visual inspection. Each chip is checked for a number of essential functions. After testing, chips which do not comply with the specifications are marked with an ink dot, so they'll no longer be used. Once they've been tested, the chips are ready for assembly. First of all, the slices are laid on a layer of adhesive film and then almost sawn through in 2 directions by a special, amazingly accurate sawing machine, so that the chips are almost separated. The slices are then carefully packaged and sent to the assembly centers in the Far East: Bangkok, Hong Kong, Manila, or Kaohsiung in Taiwan.
Okay. So, it insists very much to continue teaching. So, too much movies are also not good for teaching. Maybe I'll continue with the next topic, or what do you prefer? If the students have questions, I'm ready to answer.
Okay. Is there any questions?
I want to stop sharing. And no, it's strange. I'm using different computer, and now I can't stop sharing the screen, but okay. If they
Do you want to stop your screen sharing?
Yes, I want, but did you stop it for me? Thank you.
Yes.
Thank you.
You're welcome.
Thank you. There was a chat. Let me see. Maybe there are a question. This meeting is available. Okay, пожалуйста, send a link to YouTube, please. I will send you the presentations. No problem. If
Yeah,
you,
we will put them in the website, so I think it will not be a problem.
okay, so you have them. Okay, do not share. Oh, so if you don't at this stage, okay, it was just
Yeah, informative information.
The tendencies. This is okay. This is what happens until now, and okay. Without the break, I'll continue with the. Let's.
If you want to take a break, you can. It's not also a problem.
And I will continue with the displays.
I have one question, just for information.
Yeah.
You told us about iPhone 12, etc. Можно на русском?
Можно.
Чтобы
не знаю, успею ли ответить на русском, потому что терминологию на русском я знаю, но постараюсь.
Это больше общий вопрос. Вот вы сказали насчет iPhone 12 и от сегодняшних тенденций в микроэлектронике. А какие именно, так сказать, исследования и какие результаты ваши были внедрены вот эти вот новейшие технологии, если есть?
Значит, самая высшая технология нанометры, если у нас были, это все кончилось в 1889 году в Болгарии. С перестройкой, не перестройкой, там все, когда мы, как мы говорим, когда вспыхнула демократия, и все кончилось. Тогда в Болгарии была, ну, я тогда заканчивала университет, но в это время, в 989 году, Ботемкратия, это недалеко от Болгарии, от Софии, видимо, я тоже устаю, была огромная foundry, огромная фабрика для производства интегральных схем, и в это время мы работали на технологию 2 микрометра, это была топ-технология в мире. Вообще, в это время Болгария была, каждая страна в этом стиле, в социоэкономическом, как это было, экономической организации, Болгария, одна из специализаций Болгарии была в микроэлектронике. В микроэлектронике даже я разговаривала с коллегами, которые работали в Казахстане, которые работали, и они говорили, что они программировали, они управляли первые ракеты на болгарских компьютерах, Правец. Но это было давно. Сейчас что есть, я говорю в Болгарии вообще, и потом, что я работаю, я немножко показала, что мы работали. Если говорим о производстве, есть еще, они используют, ну, продали, уже не болгарские, она американская, другая, кажется, тоже тайванская, где были эти мощности для производства интегральных схем. Ну, это не только где были, они все новое построили, но это очень важно иметь обученный персонал. И потому что там люди были образованы и подготовлены, они там и продолжили, там, что построили. Сейчас делают, но это монтаж уже, пэкэджинг так называемый, это монтаж интегральных схем. Но больше всего это сенсоры, это датчики, и это исключительно с приложением в автомобильной индустрии. Я всегда там вожу, ну всегда, больше не могу, потому что с прошлого года с этим ковидом я, ну, больше визит нету, я всегда организую визиты моих студентов там, и они всегда так впечатляются, когда им говорят, ну, для кого вы работаете? Они говорят, для Volkswagen, ну, даже до Ferrari студенты. Значит, Ferrari. А им объясняют, а Ferrari это вообще не клиент. Они там производят 80 автомобилей в год. Вот это Volkswagen, который миллионы. Вот это уже серьезный клиент для нас. Но это в Болгарии, вообще в Болгарии, что, ну, это не только в Болгарии, это уже во всей Европе. Это и во всем мире. Это конструирование и проектирование интегральных схем. Ты можешь это везде, потому что, как я сказала, новые предприятия для продукции, они строят для каждой технологии, и даже Infineon решили, что они будут больше производить. Они покупают, это очень дорогой тоже софтвер для проектирования, это Cadence, для проектирования интегральных схем на кремний. Как вспомнила это, что это кремний по-русски. Еще ну, проектируем и потом файлы отправляем на фабрики, они производят. Ну, в Европе есть такая программа Eurochip называется, и где цены очень-очень низкие или даже бесплатно, они производят, ну, это прототипы. Это по-русски хорошо, если еще неправильно говорю, пожалуйста, помогайте.
Все.
Так, ну, это проектирование на высоких технологиях. Сейчас, ну, недавно ко мне пришли в университет, пришел менеджер, директор одной, ну, это филиал французского предприятия. Видимо, они сказали, что там из Франции, ему сказали со мной разговаривать, что они организуют стаж для наших студентов, но это тоже проектирование FPGA, я не знаю, это программируемые матрицы. Full Programmable Grid Array – это программируемые матрицы, которые они тоже делают для интерфейса компьютеров. И, ну, это тоже проектирование, но это, ну, даже производство, уже эти предварительно сделаны эти FPGA и программирование электрическое. Что это мы делаем? Я лично, такая научная работа была, это в области этих, я вот это по-русски уже не успею объяснить.
Не, можно на английском.
Вначале там еще VR-бусы внедрили, и что там это охлаждание нет, это cooling of integrated circuits, вообще, это как по-русски?
Правильно, охлаждение?
Охлаждение, ну, это охлаждение, ну, и схем, или вообще, ну, схем на более низком, или модулей гибридных интегральных схем, скажем, это так по-русски. Мы над этим очень серьезно работали, и что хорошо было, что это внедрили. Ну, другие направления, это были ну, новые материалы. Последние разработки, которые я делаю с моими аспирантами или докторантами, обычно я стараюсь делать в сотрудничестве с французской, швейцарской, с некоторым таким университетом, у которых есть возможности, есть лаборатории и есть возможность практической деятельности. Потому что для меня только теория – это ничего. К сожалению, у нас таких возможностей больше нету. Как видите, даже проекты, над которыми работаю, это больше всего в образовании. Потому что разрабатывать научные проекты в области, ну, научные проекты, это был горизонт, сейчас новая программа будет с этом году начнется. Это уже очень высокие цели там, и надо иметь хорошее оборудование, прекрасную лабораторию. Если этого нету, это не успеем. И это, когда я работаю обычно эти деньги, они говорят всегда, что деньги это для образования, эти проекты, но все-таки все равно мы используем эти деньги для научной работы, и чтобы даже они говорят, что это нельзя на конференции ехать, потому что это научная работа, все равно мы отчитываем, что больше работали, мы эти деньги не берем, а даем молодым людям, чтобы поехали на конференцию, чтобы представили и чтобы научили, и чтобы представили свою работу, чтобы получить. Так, как в последние годы был у меня, очень успешный был докторант, мы работали в Швейцарии, два были даже, один работал, я подготовила одну презентацию не о нашей работе, но, в принципе, решила, что в последний момент так решила, что интересно Internet of Things, интернет вещей, что это важно, интересно. И это то же самое, я даже студентам говорю, это больше всего коммуникации. Там есть датчики, конечно, но и даже или искусственный интеллект, это алгоритмы, это нет ничего общего с микроэлектроникой, потому что в наших днях все говорят, кто понимает, кто не понимает, все говорят об искусственном интеллекте. И говорят, и люди думают, что это какой-то, больше робота, какой-то там из Марса, который будет управлять нашей жизнью. Это алгоритмы. Я даже, когда учила автоматику, много лет тому назад, мы даже изучали эти алгоритмы, так что поэтому я решила показать Internet of Things. Об искусственном интеллекте сейчас говорить не буду, потому что это вообще не имеет ничего общего с микроэлектроникой. Это алгоритмы, это программирование будет тоже, но алгоритмы больше всего. Это самообучающие и автоматика. Так, что мы работали с первым, который с ЭТХ Цюрихом, это лучшая в Европе вообще политехника, тогда еще не говорили, в это время вообще никто не говорил о Internet of Things. Это было, это потом появился этот термин, эта терминология. Они не только, они не интернет использовали, мы не разрабатывали, а использовали датчики, но датчики, которые в виде интегральной схемы, голый чип, и монтировали, это было для приложений медицинских или для здоровья вообще, то, что сегодня очень используют, и, конечно, это не интернет использовали, была маленькая антенна, мы делали такие маленькие гибридные интегральные схемы. Я найду, если будет перерыв, найду и покажу вам изделия, которые мы сделали с ЭТХ Цюрихом. Они работали над алгоритмами, а мы сделали микроэлектронику. Это был монтаж интегральной схемы, на нашей кафедре мы это сделали. Такие миниатюрные изделия, там много датчиков было, и что человек может носить на руке, как часы, или ставить здесь спортсмены, и он мерит все, температуру, давление, разные параметры. Такие приложения были, сейчас очень много используют и говорят, что это Internet of Things, это, там маленькая антенка, и очень самые большие проблемы с этими, это мощность, это питание. Как обеспечить питание надолго, потому что они не связаны с вами. И надо было экономить там всю консумацию, нет, потребление мощности, и та маленькая антенка, которая передает сигнал. И сигнал уже есть преемник какой-то, обычный компьютер, который обрабатывает сигнал. Мы над этим работали. Еще сегодня более развитое такое приложение для... это не мы сделали, потому что это уже продукция чипов, продукция интегральных схем для диабетиков. Даже подруга моей дочери, она не живет в Германии, это в Германии налично, там ей сделать, есть в ее, не знаю, это в руке или где, в теле, такой датчик, который мерит, ну, он уже в теле, я не знаю, который мерит глюкоз все время. И есть тоже антенка, это то же самое, как то, что мы делали, конечно, еще меньше. Она может наблюдать все это на приложении своего телефона. Но что очень важно, есть маленький резервуарчик тоже в руке. Этот резервуар, и есть связь между датчиком и резервуарчиком. И когда есть проблема, а там инсулин. И когда есть проблема, он пускает точное количество инсулина, которое нужно ее. Это очень тяжелый диабет у нее. Это не такой, как у стариков. Она родилась с ними, и мы знаем, что эти люди не живут долго. Но я это рассказываю, потому что это приложение микроэлектроники, это очень важное приложение. Она может наблюдать все время. Это не как измеряют диабетики на 2 часа или все время мерить, если есть надобности, он помогает. И третья тема, над которой мы работали, это новые материалы для фотоволтайков. Ну, и вообще я пессимист в этом направлении. Они такие органические, но там, моносилиция, монокристального силиция, кремния, монокристального кремния, эффективность КПД 25% есть для в лаборатории. Потому что есть влияние воздуха, температуры, солнца, дождя, снега и так далее. 20. А в этих новых материалах это 0,6 или что-то такое, 1%. Конечно, и так пишут, вы не имеете представления, как много, извините. Простите. Пишут, и там такие публикации вообще. Если хотите, вы можете публиковать что-то такое. Это не имеет никакого значения, что результата там нету, или результат никакой, но это очень новое, и вообще он очень старался, очень много работал. Его диссертация была лучшая во всех франкофонских государств, и он получил награду в посольстве Франции, но вот это и в этом направлении я не имею намерения продолжить работать. Но фотоволтайки – это очень интересное направление. Но то же самое докторант, он сделал свое предприятие для монтажа фотоволтайков. И там швейцарцы ему обещали продукцию реализировать. Может быть, не в Швейцарии. Так, в общем линии это то, что мы делаем. Все-таки дайте мне 10-15 минут отдыха, потому что я еще это на английском, на русском. Я очень обожаю русский больше всего, я уже в русской школе училась, но это немножко устаю. Только один перерыв сделаем, потом продолжим. Хорошо? Спасибо.
Хорошо. 15 минут?
15, спасибо. Значит, так. 15-28 продолжаем. Спасибо.
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 Так, коллеги, Zoom остается на своем месте. А YouTube я буду прерывать.
Хорошо.